Okay, thank you all for coming. Sorry for the delay. This is actually a presentation that I made a few weeks ago because the last one just had a malfunction on my hard drive, and that was the only version. So this one doesn't have any of my preliminary results that I wanted to show you, but I can talk about them instead, but there will not be any graphs, unfortunately. First of all, thank you for inviting me here. It's a real honor to present this to you. And I also want to thank HB Grandi for giving me a small grant that I could use to start up my project. And the people in Hafro in Ísafjörður helped me out a lot too. Without them, I would not have been able to do this. My supervisor in Norway, Pernilla Carlson, she helped me a lot with setting everything up, and she also helped with doing the chemical analysis of my final results in NIVA. And I also want to thank Keresis in Ísafjörður. They helped me with providing an oven that I could use for my samples. So let's start. This is a general overview. I first want to talk a bit about the literature review I did, general stuff that I've come across about the marine plastics, and then afterwards go into what I actually did in my research. So, plastics. It really started when the Second World War ended. People needed something cheap and strong and durable, and the answer was plastics. The production increased a lot since then, since the 1950s, and in 2010, as you can see on the graph, on the left side there is the production volume in million metric tons, and in 2010 the production was 270 million metric tons. But because there is a problem with waste management of the plastics, so out of that 4.8 to 12.7 million metric tons actually washed out into the ocean is expected. Of all the marine debris that floats around in the ocean, 60 to 80% is actually plastics. Where does it come from? Most of it is from land, 80%, and 20% is from the ocean. And from land, the basic things are made out of the medical products that wash out into the sewage system, and then you have clothing and textile materials. So for example, if you have a fleece jacket and you put it in the dryer or in the washing machine, the small fibers will also end up into the ocean in the end. Cosmetics, you might not know that, but a lot of shampoo and scrubs and toothpaste actually have microplastics in it as well. And packaging, the food and drinks that you sometimes see on the beach when there is a lot of tourists happening, for example. Ocean-based, most of it actually comes from fisheries, because fisheries is one of the biggest activities that occur in the oceans. And then you also have the shipping industry. I haven't looked into it too much yet, because my focus is actually on the fisheries part, but they gave some numbers on the cargo loss. So per year, if you don't have any catastrophic event, like a big storm or something, 568 containers per year are lost. If you include the catastrophic events, then it's 1,000 more. But there is also research that goes into looking at the relation between microplastics and shipping lanes. So I want to look into that more later in my research. Pathways, so how do the plastics actually get from land towards the ocean, or from the ocean into the ocean? So ocean-based is pretty logical. You lose something when you're actually being there. For land-based, there are two different ways. Surface runoff, so whenever there is rainfall or you wash something off the street, that will collect in the river systems and then end up in the ocean. And then you also have sewage systems. And actually, something that I came across with is if you have different ways of treating your sewage. Normally, there are 3 different steps. You have the mechanical, biological, and chemical steps. If you have all 3, they saw that most of the plastics are retained in the sludge. Iceland actually only has mechanical treatment, so most of the plastics are washed out, because there's not, like, the sieves that they use are not small enough to actually get those small particles out of the water. before it enters the ocean. But the thing with if everything ends up in the sludge, there is actually also a problem, because in some countries the sludge is used as fertilizer. And if you use fertilizer on your land, then afterwards with the runoff, it might actually still end up into the marine environment. As soon as the plastics are in the environment, what happens? The big question is whether it floats or sinks, and most of the times that actually solely depends on the specific density of the particle in relation to the water. And in the marine system, about 60% of the plastics float because their specific density is lower than that of the seawater. If you add biofouling over, that changes, because biofouling, with the growth of small organisms on the surface, it becomes heavier and it can actually start to sink. And then something else that might influence the interaction of the plastic particle with the environment is the degradation of it, so either by the light, mechanical abrasion, or biodegradation with the biofilm. Where do we find them? There is a wide variety of where we come across the different particles, and most of the time when we see them is actually on beaches, for example, where you're just there to enjoy the nature, but there is actually quite a lot that is washed up there. They estimated that worldwide 0.4 to 6.2 particles per 50 millimeter of sediment is found on the beaches. But most of the time with beach cleanups, we don't focus on the microplastics because they're difficult to remove because they're so small. Most of the times we focus on the larger particles, and in Iceland they estimated that per kilometer of shoreline there is about 1 ton of trash. And the trash is also driftwood, for example, but the majority is made out of the plastics. And then the surface ocean. As 60% of the plastics float, they stay on top of the ocean at least for quite a while. And they accumulate in the gyres. Those are the big, I hope this also, yeah, it shows up there. So in this graph you can see the top one is the particles per square kilometer, and the bottom one is the grams per square kilometer. And then you see that this, for example, is the Great Garbage Patch in the North Pacific. It's a gyre and large-scale current in the ocean, and it pushes everything towards the middle of the gyre. Outside, the concentrations are much lower, but they're still there. And you can also see that a lot of the research, this is an accumulation of a lot of research that focused on the surface ocean. They collected everything together and made the graph here. And you can see that most of it actually focuses on the northern hemisphere. Something they saw in the surface ocean is that over the years it actually didn't start to accumulate. The small particles didn't seem to increase. And there's several things that they think might have happened with the breakdown of the particles, that they are so small that they don't end up in the sampling nets, which is a big theory in there. But there is also research that looks into deep sea sediments. And they saw, if you compare to shallow sediments, that the deep sea sediments has quite a lot more microplastics than the shallow sediments. So it might be that that is another hotspot where everything starts to accumulate after it settles down to the bottom. If you compare it to the surface ocean, that concentration is a lot less. As we're in the Arctic, this might be of interest. What about plastics in ice? You need to be careful with what you think when you see large numbers like this, like the 12,000 particles per liter, because it might be that they extrapolated and then it ends up with a high number. But if you compare it to some other research, still the number is quite high if you compare it to the number that we saw for the surface ocean, like 16.2 particles per 50 milliliter is quite a lot more than 0.000 or something. The Alfred Wegener Institute looked at the origin of the particles that they found in the Arctic ice, and they could trace it back to the Great Garbage Patch, and to shipping industry. So they found particles that belong to paint of the shipping industry. And my question when we think about ice is always like, what will happen when there's a lot of melting of the Arctic ice? But my research is not into that, but it's an important question to ask. Impacts. I haven't looked into the socioeconomic costs yet, but you can imagine that if you have a beach where a lot of tourists comes and you see a lot of debris, it's not very attractive for the tourists, so it might get an impact there. And also if you want to clean it up, that takes quite a lot of money as well to do. This is actually a picture that I took when doing a beach cleanup on Hornstrandir, nature reserve up north. And we collected 9.5 tons. And I think the stretch of land was about 5 kilometers. And most of it was from the fishing gear. A colleague of mine is actually looking into the litter on beach and then compare it to what is known in the fishing industry as well. But for animals, I mean, I know a bit more. You can probably imagine that this is not really good for the animals. It inhibits their fitness, it affects their mobility, and it might actually lead to death because they can't move as they should. Something else that you might not see as much is the ingestion of particles. Most of the times you only see it when this happens, where there is a bird on the beach and you see that they had a lot of plastics in their guts. Something that I didn't know is actually that turtles, they eat jellyfish, but if you have a plastic bag floating around in the ocean, they don't see the difference, so they eat it and it blocks their digestive system and it will fill up their gut so they don't want to eat, and then eventually they can die from it too. And then there's the question if it ends up in us. Do we have plastic in our guts? And if I remember correctly, the agency of Austria, Environmental Agency of Austria, looked into this, and they had 8 participants from different continents. They saw that each of the participants had plastics in their stool samples. So we actually do have plastics, and it might be from what we have in the living room or something that we ate. They don't know that one yet. But yeah, some of the unknowns that I've come across up till now is the biggest question, of course, toxicity. How toxic is it for the environment, for the organisms that eat it, and for us, of course? And what they found is a bit contradictory. Laboratory results show that, yes, it can be very toxic for the organisms, but then some studies in the environment, field studies, they say the concentration is not high enough to actually have an impact on the organism as severe as they saw in the laboratory results. So I would say this needs more attention to give a clearer answer on how toxic it actually is. Then the question of whether it accumulates in the food chain. Most studies only look at 1 or 2 species, kind of like what I did. I looked at 2 different commercial fish species here in Iceland, and they don't look specifically into food chain. But if it starts to end up in all different kinds of fish along the way, and also in the big mammals, for example in whales, you can imagine that there is a build-up. But they need to look more specific into actually the chain to be able to answer that question. That's something I already mentioned earlier, the Northern Hemisphere bias. Could be because most of the people actually live on the Northern Hemisphere, but it does create a problem when you try to estimate the total amount of plastics that are in the ocean if you don't have enough data from the Southern Hemisphere too. And then appealing organisms. When they started this research several decades ago, they first started with marine mammals and with birds and things that people can associate with more. Luckily, in the last few years, they actually started also looking into fish and invertebrate species, something that we actually eat. And then the last one, limited research on plastics in Iceland. I think, from what I've heard, it's like maybe 10 different studies have been looking into a aspect of plastic research in Iceland. And I'm glad to say that the government actually is proactive. They set up a plan with 18 steps, I think, to start phasing out some of the stuff in the stores so that it doesn't end up in the ocean from this side. So even without the limited amount of research, they want to make a change. Still, it would be good to know what the status is to compare it to others as well. And that leads me to my thesis. My question is, what is the plastic occurrence in Icelandic cod and saithe from the west coast of Iceland? The sampling, I actually had a picture here where you could see the stations. I focused on the west coast because that's where I could join on the cruise, the Árni cruise in spring for the groundfish survey to get the saithe. I couldn't get the cod there, so I had the 14 stations from saithe were from that location, and then the cod was from one location because we had a limited amount of time to get it because it was summer holidays, and there was a very high market demand, so it was difficult to get a hold on to a sample. So that was one location. And that's done. The processing in twofold. What I'm going to talk about is actually only the first part, so I'll skip over the second part because I still need to work on the data for that one, but I'll mention it here. So the main one that I worked on is the alkaline digestion, which is the potassium hydroxide, and I made a solution, 10% solution of it, and then I would add it to the stomach samples, like the gut system samples from the fish, in a ratio from 1 to 6. So 1 for the sample weight and then 6 for the KOH weight. I would incubate this for 24 hours at 60 degrees and then add citric acid afterwards to neutralize the sample and clear it up, because when I did a small trial, I could already see that the filters that I used easily clogged if I didn't do it. So it would help with the filtration afterwards. I let it settle for another 24 hours to let all the big particles settle to the bottom. Then I filtrated it over a glass filter with a very small pore size, and in total I actually think that number changed, but it is still, if I remember correctly, it was like 54 saithe and 38 cod. Then I also want to compare it to a different method, an easier method in the sense that you don't need a lot of materials from it. So it was just having 2 kitchen sieves, a lot of water, and scrape out everything from the gut, put it in the sieves, put a lot of water on it, and then pick out the stuff that I thought was plastics. And I processed 38 saithe and 32 cod from that one. That's done too. Analyzing. I've been using a stereo microscope to do the first visual analysis, and my supervisor and a colleague of mine in Norway, they did that too to verify my data. And we recorded the category and the color, and then I tried to measure the length as well. And then in Norway, it's not the NIR that they use, but the FTIR. It's basically using a different sort of microscope that looks at the chemical composition of the particles to verify whether it is plastics or if it's biological. And then afterwards I analyze it with R to look for relationships between the species, locations for saithe, and the size and weight of the fish to the abundance of the plastics, the total amount of plastics found in the fish. I had to use a Kruskal-Wallis test for this because my data didn't meet the assumptions that you need to have for the ANOVA test, so it's a non-parametrical test. It's in process. The contamination protocol that I used is very important because in a lab there's always dust floating around with fibers in it. So to be able to see what I had actually in the sample to verify what my contamination was, I had several things that I did. So I would be wearing nearly 100% clothing so that if their fibers were actually from me into the sample, it would not be plastic based. And then clean the environment that I worked in regularly and used lab materials, cleaned the lab materials in between too. And then I also used aluminum foil to cover my jars where I had my samples in, because the inside of lids of jars most of the times also have like a small plastic film, so you can't really use them, otherwise you might contaminate your samples too. And then I also had a lot of blanks, which is basically just a Petri dish with a coffee filter in it, and then I would make it wet so that everything that fell out of the air would collect in the Petri dish, and I could match the Petri dish to each individual sample. I had one for when I was doing the sampling, and I had one when I was doing the actual processing in the lab. Then I also had a procedural control, so that's everything the same except you don't add the stomach sample to it. And if you sum everything up, I would know what the contamination was in the area, and I could subtract that from each individual sample to get some final results. I'm not going to do this yet. As I said, I don't have any graphs, but I can tell you more or less what I found. There are no relationships that I found between the species and the total amount of plastics, the location of the safe and the amount of plastics, the size, the weight, the condition factor, which is a measure of fitness. Like if it's lower than 1, it's a not healthy fish. If it's bigger than 1, it is a healthy fish. And there was another one that I looked into. It will probably, gut fullness. So I measured if it's empty, half, or full. None of it had any relationship with the total amount of plastics or the category of plastics that I found, like fibers or fragments of that. Then let me see. I don't know the exact numbers, but I looked at the plastic occurrence in total to answer my research question, and it was for cod around 17% and for saithe a little less, 16% more or less. And if you compare that like to the other studies that I looked into along the Norwegian coast and along the Canadian coast, their percent is 3% of the individuals had plastic in it. I need to look into whether they also included the fibers or not. It might be a decision that they made that they didn't include them. But they also had research along the east coast of Greenland, and they actually had higher percentage concentrations than I did. So it's interesting to see that along the outlines they had lower, but I need to look into what they actually recorded for it too. Then I had a graph that looked at the color, like what the cod had as color of plastics in their guts and what saithe had. Both of them had green, black, and gray. And then saithe also had pink and red, and the cod had a bit of brown in their guts too. So I want to see if there is more research on it too in some other studies that looked at the color in there. But I think that probably my samples just ingested it by random because there's no relationship between anything. So if they had it random, it might not matter like which type of plastics ended up in their guts as color-wise, that they didn't choose it, for example. Yeah, I don't remember exactly else what I could tell you about the results now. It's also ongoing, so I still need to look into all different kinds of stuff. But lessons learned so far, this is a bit like what did I learn in general from using the method, the dissolving method, is that the contamination protocol is really important because it's the only way that you can verify what you had floating around in the environment and see if it also ended up in your sample. And they did some research on like different devices that you could use to limit your contamination. So you could think about a fume hood, for example, but the fume hood wasn't necessarily much better than just having a work environment that is open, because the fume hood sucks everything in. So it might actually get everything in there. The only one that excluded quite a lot of the contamination was the, I'm not sure how they call it again. It was like completely closed off environment where you would work with gloves in, for example. That was the only way that they could exclude it a lot better than with the other methods. So yeah, the protocol is really important to be able to verify. And then something I ran into is that you have gut stomachs are quite fatty, and with the KOH they react, and they, if you put them in the oven, the top layer started to burn, and it created a very brown layer, or yellow, whitish layer. So then it was difficult to filtrate because the pore size is so small. And I would use a blunt object to scrape over the filter so it would actually suck through. There were never any holes in the filters, but it's not easy to afterwards analyze the filters anyways if there's a lot of jelly stuff going on. So that was something that I ran into. And chemical analysis with the FTIR, which are some results I also still need to look into. They are invaluable. You really need to be able to, if it's that small, like the microplastics, nanoplastic size, you need to be able to do the chemical analysis to make sure that it's not your eyes tricking you, that it looks like something plastic, but it's not. These are some filters that I took a photograph of. This is actually like one of the clearest filters you would get. It's like a lot of granular stuff on there, but it would be pretty easy to actually see the particles if they were there. And then this one is not as clear because there was aluminum foil that was reacted with the KOH, and it would fall into the sample. It doesn't matter for like the chemical analysis because it's aluminum, but it does make the vision under the microscope a bit obscured. This is what I was talking about with the fatty stuff. It is a lot of jelly stuff that it would be difficult to see something. And then we have this, which is a skeleton from a crustacean. It didn't dissolve in the KOH, so if I didn't take care, it would actually flop out of the jar into my sample. So then it was also on my filter, and you had to move it around to be able to see something. If I would have to add something to my method, it would be that I could only decant the top layer, because then afterwards it started to clog, and I didn't want to scrape the filters. So it would be better if you then also store the rest of the jar, so you can sieve it over a fine sieve, so you can see if there's anything left in the residue. I did something similar like it. I would store it and then put it in a petri dish and look through it under the microscope, but I think it would be better if you also completely sieve it, because then you don't have any liquid left, for example. Also something to take care of is using plastic materials. I had a filtration system that was completely made out of plastic. So I did some runs in the beginning where I would look for contamination of the system itself. The only thing that is in contact with the sample is a top bit, and that was pretty clean. But then if you would rerun the water through the filtration system, you could see that somewhere in the tubes there was also some stuff floating around. So I recorded that in the beginning so I could later subtract it as well. So if it's possible, use everything glass. It will limit your work in the end. I think that is it, and I would like to thank you for your attention. If you have any questions, I will be glad to answer them as well.
Yes, we have time for questions, but please use the microphone.
So in one of the first slides, you compare the amount of plastics in Europe and the rest of the world. Do you think that the stability in the last years in Europe are due to the stability in the population or in the degree of development? As in, as when we get more developed, we start to use less plastic and even go into a trend of reducing and using other kind of materials for packaging and...
You mean the graph with the production, like worldwide production compared to Europe production? I think actually that both of them have been more or less equal, growing equal over the years. Europe has definitely started to use different substitutes for plastics over the years, so it might influence it a bit, but I don't think a lot yet, because they're just starting with it. Really.
So you don't think that in the, let's say 5 years, we will see receding, like starting to go down actually, instead of growing, here in Europe at least?
If we continue like we are doing now, then I think you might actually start to see it properly on the graph. But it's a million metric tons, so you actually need to start to decrease quite a lot before you will see it, I think. But yeah, they are moving towards it, so
right.
Yeah, thank you.
What about the possibilities of removing the plastic from the ocean?
There are several ways that they're looking into. I think the one that most of us know is the big cleanup that they're doing on the Great Garbage Patch in the Pacific, and it's a floating device with a net system underneath it, with quite big holes actually, so that all the marine life, the big marine life, can go through it, and also the small phytoplankton and such. And they gather everything together, and then they compress everything and move it back to land where it's stored. So that's one of the bigger ones that are actually just deployed. But the thing is, that is focusing on big plastics again. I'm not sure if there is anything of yet that looks into removing the microplastics, because if you think about removing microplastics, you also have to think about what is the impact on the phytoplankton and the zooplankton, because they're so small in the same size range. So I don't think I've heard of anything yet, if that answers your question.
So there is no solution to get out of the ocean all these millions tons of small particles in the
Small
ocean?
particles, not. I think there is hope for the big particles, but they are everywhere. So I think as of now, they're looking into the big hotspots that they know, like the gyres, and collecting most of it from there. But yeah, outside of the gyres, you also have quite a lot of plastic, but they're really sparse. So then if to try to clean them up also takes a lot more money. So yeah.
More questions? Yep. Is this correct, Anne, by the way?
More or less, yeah. I remember A17 and A16.
So when you were talking about the color of the plastic in the stomach of the fish, you mentioned that they ate brown and gray and green. Didn't you see any red or yellow? Is that because the fish are choosing the plastic? Because it looks like their food, or are they just these colors degrade faster?
I don't think they actually chose the plastics, because the fish that I looked into, they were like, the smallest saithe was 48 centimeters and the smallest cod was somewhere in the 80s. So that is big, and they have big mouths, but the plastic particles that I found were minuscule. They were in the microplastic range, and that's smaller than 5 millimeter. I don't think they chose them, so it's just randomly ingesting. I want to look into the literature and see if there is a recording of like the ratio between different colors of plastics found in the ocean, because that might be an answer to the question, like, why did it end up in the ratios that it ended up in the fish? But I don't think they actually chose for the colors.
Thank you, Anne, for very nice talk, and thank you for coming. I was wondering about the method that you choose. Why did you choose it?
The biggest thing with microplastics is it's really difficult to get them out of the stomachs. They're so small. and really difficult to see. That's also one of the experiences that I had with the second method that I didn't talk about a lot, is that it's so difficult to actually see what is plastic and what is not. And with dissolving the stomachs, you dissolve everything that's in there, and then you'll have the plastics floating around in it. So the idea is that if you filtrate it, you'll capture way more than you actually do with just looking through the sieves and picking them out. And from my experience at least, I think that is definitely the case, because it's more expensive because you have to buy chemicals and you need to have a filtration system as such. But it is more efficient in the way of collecting your data in that sense.
If I can, a related question, how, internationally, how similar are the methods and defining microplastic, for example?
Quite varied, actually, and it's a problem for comparing different methods, because if one uses a different ratio, for example, because I actually had to choose a different ratio than they did in the literature. They said 1:3 would work, but when I tried that out in a pre-trial, it didn't dissolve everything. It was really difficult to filtrate. So then I tried 1:6 and 1:10. But the thing with 1:10 was that I didn't have enough materials to get my sample size right. So then I ended up with the 1:6, which was efficient, which is again different from what everybody else did and difficult to compare. They are trying to align them more. So there are quite some studies that look into like different methods, which one is most efficient, and the KOH comes out most of the time. So then the next step would be like, okay, which is a good protocol for all different fish, because cod is very fatty and might react differently, but is it still efficient enough to use the same method in that sense?
So as it is, it's difficult to compare, Iceland with Norway and etc.
I think because I still use the same chemicals, it is okay to compare. Because they found that if you use KOH, you don't degrade the plastics, which in some cases, if you use a certain acid, actually does. One of the plastics that started to degrade was that one that you have in the cigarette butts. They were dissolved if you used, I don't remember the name exactly, a acid method that they tested. And then if they compared it to the KOH, they saw that it didn't degrade. So it is one of the better ones that doesn't affect the plastics as much, so you can get more out of the data.
Yeah, maybe one more question.
If I remember correctly, so you mentioned that it didn't matter how many plastics in relation to stomach fullness.
Mm-hmm.
Why do you think is so? Is that means that it accumulates in some way in the digestion tract, or?
Well, my idea was that if you have an empty stomach, you don't have a lot of plastics in there, compared to a stomach that's full and had food, so might have more. But I think because it was just randomly ingested in the first case, then it's also probable that it's just because they opened their mouth at one time, even if their stomach was full or empty, and it just ended up there. So I want to see if other research looked into the same thing. I haven't had a chance to do that yet. But yeah, if they did find a relationship, then I'm curious why I didn't, in that sense.
Okay, thank you, Ann.
Thank you.